toward addition chains and numerical invariants of non-associative algebras. So you can start your talk, Alexander.
Mm-hmm. Thank you very much. First of all, I am grateful to the organizers of this event for the opportunity to give a talk here. I'm very honored. I will be speaking on recent and results obtained during the past 20-15 years, together with my students, current and former students, Svetlana Zhilina, Olga Markova, Dmitry Kudryavtsev, and even the student of my student, Mikhail Hrystik, whose supervisor is Olga. Also, my colleagues from Ljubljana, Gregor Dolinar, Bojan Kuzma, and Polona Oblak. My colleagues from Dublin, Helena Šmigic and Tom Laffy, and colleague from Berlin, Volker Merman. Anyhow, before I will go into the details, I would like to show you a little bit flavor how this theory is working. So we all know that if we would like to generate space of matrices, then we need n square matrices where n is matrix size. These are nothing but matrix units with one on the intersection of I, row and column correspondingly, and zeros elsewhere. So here there are two operations: addition of matrices and multiplication of matrices by scalars. And using these two operations, you need n square matrices. But let me add the third operation, namely the matrix multiplication, which is quite natural here. How many matrices do we need to generate set of matrices as an algebra? This is our next question. Well, certainly we need less matrices. Like, for example, this exercise will tell you that you could always exclude E11 from operations according to that formula. Use product. Well, you could exclude all diagonal matrix units the same way. You could use rules of multiplications for matrix units and exclude much more. But how much further down you could go? Well, when you will start to analyze this question, you will immediately see that first, matrix units are not the best possible here. They are quite thin in a way. Words in matrix units, when you form products, will not generate a lot. So it is natural to consider the problem from the opposite side. Instead of going down with existing number of generators, just to see what is, say, if I have one matrix, is it possible to generate algebra of matrices? Certainly not, because there is a Cayley-Hamilton argument saying that maximal space that could be generated in this way is n-dimensional. So not matrices. Well, one is not okay, maybe two. Well, at first glance, this sounds like next question line, but it turns out that the answer is positive, and this is quite surprising from many points of view. In fact, it is very nice that matrix algebra is generated as an algebra to compare with n square for the vector space. And here I just gave a couple of matrices. So this matrix unit E12 together with what is called cyclic matrix. Here I take identity matrix and form a cyclic permutation of columns. So this couple could generate matrix algebra, and this is even analytic formula for all matrix units, which tells you that it is possible to generate all of them in the following way, as you see the steps of this form. Well, there are many other couples that could generate matrix. Assume in your field you have nth root of unity. Then the first couple written here could be also considered generator. Or if your field is of characteristic that greater than size, then other couple written here is a generator. And each time I could write explicit analytic formulas for matrix units. Moreover, with probability 1, any couple of matrices could be a generator of matrix algebra. So as we have seen already, it is very important how these words in generators behave and how the span formed by these words, linear span, how fast it grows. So then it is important to analyze this somehow numerically. For this reason, we consider what is called the length function. So let me go through definition briefly. We start from finite dimensional algebra over field. And of course, it is finitely generated. So there is a certain finite system of generators, S, with A1 and up to AK, these are our generators. And we consider words in that generators. So this is the length of the words is just usual length of word, the number of letters, and we also consider spans. So we consider span of words of length less than equal to I, and denoted by Li over our generating system. So it appears that there is a certain flag of subspaces, words of length not greater than 1, they are embedded into words of length not greater than 2, and we start from a particular generating set and form this flag, where unification of all elements will give us our algebra. But it turns out that since our algebra is finite dimensional, then certainly should be certain stabilization in this filtration. Here, if we don't have equality, then there is a growth of dimension at least by 1. And since our algebra is finely dimensional, should be a stabilization. One important but certainly trivial observation is that if this chain of subspaces over associative algebra is stabilizing at certain step, so subsequent LIs are equal, then it stabilizes forever. Well, just easy inductive argument. We singled out word of n-1. We know this coincidence, and using such coincidence, we show that the word, arbitrary word of the next subspace is nothing but the original. It belongs to the words of existing index. But I would like to point out that for non-associative algebras, this does not hold. Just look at this example here. We have such an algebra generated by these 4 generators. The first one squared is equal to the second. The second one squared is equal to the third. And finally, the third one squared is 0. All pairwise products are 0 as well. So if we consider it as a generating system, E1, then certainly space spanned by words of length not greater than 1 is here. L2 is here. And if we consider words of length 3, I wrote them here. You see that they are all 0. So if we consider L3, the span of all words in generators of length 3, then you see nothing more, nothing new appears. So L2 is equal to L3 here, but this is not the whole algebra. To obtain the whole algebra, we need the words of length 4 in generators. So only this way you could remember our generator is E1, and only considering its 4th degree, you could obtain the whole algebra. So in non-associative case, this phenomenon is not true, and equality between subsequent members will not guarantee the stabilization. Well, now we could try to make the length function not depending on the given generating set. We remember that for any generating set, there is a clear upper bound, which is dimension -1, according to our previous considerations. So there is a correctly defined maximum over all generating sets for the first step where this chain is stabilizing. So length of an algebra is certain max-min function. Maximum is taken over all generating set, and minimum is nothing but the minimum in that chain where the first stabilization happened. So at least for associative case, the definition is ready. And This actually the last bound I just mentioned, dimension -1, is certainly sharp. For example, if we consider group algebra of a cyclic group of order n, then working with that generator, we achieve this bound. Well, that inequality could be strict as well. We compute the length of triangular matrix algebra, and it is less, it is equal to n-1, and it is certainly less than dimension of triangular matrices -1, which is quadratic number. And it's quite easy to show this. Just this particular equation will give you linear dependence equality, which will allow you to reduce long words, words of length equal to n. And these are generating systems. This is a set of generators on which this bound is achieved. n-1 bound for triangular matrices. So we have such a bound, but still computing length function is very non-trivial. Just look at this 2x2 example. So we have matrices, 2x2 matrices. Even computing the length here is not evident. First of all, we know that generating set could be always assumed to be linearly independent. Otherwise, we just remove dependent garbage by these equalities, which will provide dependence. And then the first observation here is that dimension of L1 is should be at least greater or equal than 3. Certainly, this is true by Cayley-Hamilton argument. If it is if it is less than 2, then we simply don't have a generating set. But even understanding this dimension, we still have a number of possibilities. So in case it is 4, so we have possibilities equal 3 or 4. In case it is 4, then we already have whole matrices, whole matrix space, and the dimension, the length of this generating set is 1. But if it is 3, 2 other possibilities appear. In one possibility, we have generating system when giving us 2, but in possibility where dimension of L2 is less than 4, we just have the system which is not a generator. So finally, we have that bound for all generating sets. It is bounded by 2, and this bound is achieved on that particular set of matrix units. Well, I better mention that, say, for 6x6 matrices, the problem is open. And length was considered from the beginning of 60s in the work on mechanics of isotropic continua. This was paper by Spencer and Rivlin, who were trying to parameterize certain mechanical problem using tensors, and computing those tensors, they arrived to the question of length computation for 3x3 matrices. Later on, it was Azaria Paz in 1984 who proved the first bound here, the quadratic bound on the length of matrices. After that, Christopher Papachena in 1997, using already 2 parameters. So the dimension of algebra, which is already finite, and the maximal degree of minimal polynomials. Using these two parameters, he established the following bound, which is, say, in the case of matrix algebra, it is n to the power 1.5, better than quadratic. It is important to have these bounds. As I mentioned, it was already used for tensors, but say in quantum studies, people consider a lot Q-commutative matrices. So AB is equal to QBA, and this quasi-commutativity could be considered as a condition that words AB and BA are linear dependent, and this relation is turned out to be very important for quantum studies, and in particular studying the length of this couple as a generating system is important. To give another more concrete example, let me consider here purely algebraic, even linear algebra problem. It is important for many problems to check if our two matrices are somehow related. One of these possibilities is so-called unitary similarity. So similarity by a unitary matrix. There is well-known Specht criterion saying that two matrices are unitary similar if and only if traces of corresponding words written here, where A star is nothing but conjugate transpose of complex matrix, are equal, but for all words. Nice numerical criteria, but it could take forever to check coincidence of these traces for all words. It was Pearcey in 1962 who said, no, this is a finite criterion. Specht criterion is a finite criterion. So there is a particular degree bound here, and you could check words only, you need to check words only up to certain value of degree. Later on, Alpin and Kramov found similar criteria for unitary similarity of matrix families, unitary congruence of matrices, and so on. And they found a link from this degree to the length of matrix algebra. So the length was serving in that problem as a bound for degree of words which you need to consider in that particular problem. Well, and we have still easy low bound because of this couple of matrices. For this system, we have simply n minus 2 value of length. Well, these are nothing but direct computations with understanding that these two matrices are Q-commuting. Well, but there are two conjectures. The first one is the length is linear, and the second one is the length is that particular function. So there are different works, a number of bounds, but the conjecture is very interesting and still open. I would like to point out that for some particular set of generators, this conjecture is true. So let me take non-derogatory matrices. So matrix is non-derogatory if minimal polynomial is equal to characteristic polynomial. So these are examples here, and algebra generated by non-derogatory matrix has the following length. And recently, together with Olga, Elena, and Tom, we proved that if our generating system contains certain non-derogatory matrix, then the conjecture is true. So the conjecture of path about the length is true if the set of generators contains non-derogatory matrix. Together with Olga and Volker, we were able to establish even better bounds for Q-commutative generating system. I will not go into details here about generators, but let me pass to classical algebraic constructions. For example, direct sum of algebras. There is a result of Olga Markova saying that we have upper bound and low bound written here. In fact, these two bounds are sharp. So we could consider nil triangular matrices and diagonal matrices. So it's not a very difficult exercise to compute their lengths and to realize that if the field is sufficiently big, diagonal matrices have length 1, and this bound is achieved again on certain particular generating sets. And when we consider the sum of two nil triangular matrices, we can achieve low bound in this inequality for direct sum. And when we consider this particular algebra, summation of two triangular matrix algebras of size 2, when we obtain upper bound. So the inequality here is the best possible. I also would like to pass to other algebraic constructions briefly. For example, homomorphism. Length behaves well with respect to homomorphisms. So there is if we have homomorphism, then there is length bound. Even more, of course, isomorphic algebras have equal lengths, but certainly not the converse. For example, here we have certainly equal values of length, but the converse, there is no isomorphism. And on the other side, this inequality between length of homomorphic image and length of original algebra could be really strict. Say, if you have diagonal matrices over small field, then this is a case where you have clear homomorphism from triangular to diagonal, but strict inequality for length. Well, so behavior seems to be classical, but we arrive to the following unusual and nice example. When we check behavior with respect to taking subalgebras of our algebra, we could easily find out, well, not that straightforward, but still, but length of subalgebra could be greater than the length of original algebra. So just to give you a certain example, this is A4 is an algebra of length 2, which could be directly shown, but we could find subalgebra in that A4 generated by non-derogatory matrix. So this is non-derogatory matrix in form, in fact, here, and that is why the length is dimension -1, which is free and greater than length of original algebra. So, in fact, iterating this idea, we were able to find out subalgebras which have length which is greater than the length of original algebra for any A. And Olga later on worked with quotient. So we could even make this quotient arbitrary. Another thing is that working with upper bounds, and this is a very useful result proved by Olga, working with upper bounds, we could always assume that our field is algebraically closed because length of algebraic closure is in fact greater than the length of original algebra. And of course, equality could be achieved and could be strict, as the following two examples show. Well, the next comes, we are dealing with finite dimensional algebra. So these are Artinian, and we have radical, Jacobson radical, which is nilpotent. Why not to compare these two numerical invariants? We started with local rings. So ring is local if all non-invertible elements of that ring form an ideal. And this ideal is nothing actually but the Jacobson radical. And there are other equivalent definitions. And it turns out that for local rings, using nilpotency index of radical, which is IA here, we could bound the lengths. Later on, it was Olga who proved more general bound for an arbitrary algebra. Right, with a previous bound and exact, I mean, which is sharp. To see this, you need to consider so-called Schur algebra, having such a block structure where these are identity matrices multiplied by x. For commutative algebra, for commutative subalgebras of matrix algebra, it was Paz who proved the linear bound. However, we were able to characterize the extremal case. So it turns out that the following three conditions are equivalent. Length is equal to n-1. So maximality with respect to the length function, maximality with respect to inclusion is equivalent to it, and the fact that algebra is generated by a non-derogatory matrix. Well, there are many different terms to fill this extremality of commutative subalgebra. For example, in terms of centralizers, so So the centralizer of a matrix of an element is nothing but the set of elements commuting with it. And minimal centralizer, we call the matrix minimal if it has minimal centralizer with respect to set inclusion. This is one ingredient we need. And another ingredient, another language we need to characterize this extremal case is the notion of graph, which was already defined in the talk. We just consider certain algebraic structure and define commuting graph. We have an H in that possibly infinite graph if, say, our elements commute, and otherwise no H. In classical way, we could define path, distance in that graph. And so, for example, distance between two vertices, which are, say, nothing but matrices, is a minimal number of edges in any path connecting these two matrices. And then the following result, which is due to, which we proved together with Polona Oblak, Boyan Kuzma, that over algebraically closed field, the following 9 conditions are equivalent. Well, some of these implications are sure. So certainly not all implication. It was not we proved all these implications, but maybe collected them. So non-derogatory matrix is nothing but minimal matrix. This is equivalent to the fact that centralizer is equal to a set of polynomials in A. The fact that f of A is maximal commuting subalgebra. The fact that A is one regular, meaning that each eigenvalue has geometric multiplicity 1. In terms of Jordan normal form, we have the situation when to each eigenvalue we have just one Jordan block. Existence of cyclic vector is also equivalent, and the algebra is maximal among all commutative subalgebras of matrix algebra. And finally, in terms of distances, should be a matrix such that in commuting graph, the distance is equal to 4. In fact, the diameter. For larger fields, where the number of elements is greater than 4, it turns out that first 8 conditions are equivalent, and we proved this, but the condition number 9 is not any longer applicable because, say, over rational numbers, the graph is even disconnected. When we speak about commutative algebras, I would like to mention the following interesting bound proved by Olga, giving the upper bound for any commutative subalgebra. Here we have integer part and difference. So better than natural bound, but still for any particular algebra to compute the length is rather non-trivial. Even say for group algebra of abelian groups, if we have this condition satisfied and the field is sufficiently large, greater than size, then the length is nothing but the order of a group -1. And this is, in fact, follows from the fact that such group algebra are one generated in most of the cases. But if the field is small, we have the following length, which is related to the previous bound, and in modular case, where characteristic is equal to p, we have the following computation for the length, and it could be easily shown that the length really depends on the field, as you see it here, even for particular examples, which we obtained together with Olga and Misha. And as you see here on this slide about dihedral group, recent work of Olga, we have such a value of length. But if we say consider case of field with two elements, length goes down. If we consider another group of 8 elements and its group algebra, namely group algebra of quaternions, when again length depends on the field. Namely, we have such an interesting invariant as level. So the level of a field is the least positive integer such the following equation is true. So it is Pfister theorem saying that such number is always power of 2 and each power is realizable. But it turns out that really, if the level of a field is 2, we have one value of the length of group algebra and another value otherwise. Well, now what happens in non-associative context? Here, of course, the order of multiplication is important, but we still could proceed defining the length of generating set, and then we could consider the following question. As we have already mentioned, coincidence of two subsequent LIs will not lead to complete stabilization in general in non-associative case. Let me just remind you this particular. But you may ask the following natural question. Okay, Alexander, if two elements coincide is not sufficient, but maybe sufficiently many elements, if they coincide, this will be sufficient. Well, there is an answer. It turns out that the following coincidence is sufficient for global stabilization. So from n until 2n. And then global stabilization is guaranteed. It's rather straightforward inductive argument to show this. And then considering a worst case degree of words possible in non-associative algebra, it is possible to obtain the upper bound. So for algebra of dimension n, the length is always bounded by 2 to the power dimension minus 2. And this is a bound we established recently with, together with Dmitry Kudryavtsev. And we also proved that the bound is sharp. Just considering this algebra with such a system of generators, we realize it is in a way worst possible algebra. I mean, in terms of generate. the whole algebra. Well, now we pass to some constructions like Cayley-Hamilton construction, defined in a way, and arrive to the first example of non-associative algebra in a natural way. So we started from non-commutative case of invariants, and the length here is 2. Still, one need to show this, but it's rather straightforward. I would like just to mention that this 2 is achieved on this generating set, which is natural. For octonions, this is the first non-associative case, non-associative example. We have already 3, and it is achieved on this generating set of these 3 elements. And I would like to mention that together with Svetlana, we recently considered all unital composition algebra and computed the length in that case. And also we considered standard composition algebras, one of the following 4 subalgebras constructed from original algebra, and again computed the length here. Another result obtained together with Dmitry Kudryavtsev is about finite dimensional Lie algebra. It turns out that there are many algebras, in fact, whose lengths behave similar as the lengths of associative algebra. So for finite dimensional Lie algebra, we have this bound dimension -1, and this bound is sharp, as you could achieve this on the following filiform Lie algebra. Another thing is that, of course, for any associative algebra, we could always construct adjoint Lie algebra, and given a generating set of this Lie algebra, it is possible to obtain bound for generating length of generating set for associative algebra. But for generated sets, if we consider lengths of both Lie algebras and associative algebras, then all possible situations can happen. Like here, we have coincidence of lengths. We consider Cartesian product of real numbers, degree 2, and corresponding addition and multiplication defined coordinate-wise, and corresponding adjoint Lie algebra. It is abelian, so the situation is as I mentioned, and but we could have other inequalities. This was a case of equality, but we could realize both other possibilities. Length of associative greater or when smaller. I will not go into the details for the lack of time, but I would like to mention when there are many classes of classical classes of algebra with algebras where the growth of length function is similar to associative case. Here I just mentioned Leibniz, Novikov, Zimbiel algebra, Maltsev algebra, where the bound is similar to associative case. Well, this was described in talk of before, so I will not go into the details, but I would like to mention that the important tool to study length in non-associative case is the following characteristic sequence. So we put the index k where the first jump of dimension happens as many times as the value of a jump in this characteristic sequence, and we start from 0. So define this sequence inductively, and it turns out that the last member of this characteristic sequence is equal to the length. Also, we could associate a certain basis of reducible words to the given. So having some non-associative algebra, we take its generating set, and we could associate, we consider its characteristic sequence, and we could associate a certain basis of reducible words. And there is a correspondence between number of these words and elements of characteristic sequence. And considering evaluating these irreducible words of a basis, we arrived to the following interesting combinatorial feature of a characteristic sequence. It turns out that any word would be decomposed into the product of two reducible words, and the length is additive. So we arrive to the notion which is usually called addition chain. So such a sequence where any element is a summation of two previous elements, possibly not the last previous. So we compute a certain integer n in a certain chain of addition, and the length of addition chain is the number of sums needed to express all its numbers. So for example, here you would like to express 31, and you start from these elements here, and finally obtain the result. Well, this is classical combinatorial notion, the addition chain, and you could find it in many well-known problems. For example, when you would like to weight a large amount of some goods, and you have a certain scale, a certain weight of 1 kilogram. Certainly, what you could do is always comparing certain amount of say sugar with 1 kilogram weight and add it to the quantity you measure, but this is suboptimal. It is much more optimal to consider to go via additive chain. So meaning that now after first measurement, you have already 2 kilogram value achieved. So, and you could use this information, and you could use all the previous information on the next steps, and finally arrive to quite optimal technique to make weighting. The same works, say, for exponentiation, for the first exponentiation. I will not go into the details. It is much more easy to compute powers using additive chains, in fact. And these studies, additive chains is important subject in combinatorics, and so in this situation, for example, there is Brauer-Scholz conjecture about length computation of additive chain, which is still open. But it turns out that such behavior of characteristic sequence of non-associative algebra allows us to consider it as a and allows us to characterize it in certain combinatorial terms. So we define certain notion of proto-characteristic sequence. Here, consider that it is monotonically non-decreasing and have this behavior of additive chains with few other details. And the nice fact is really characteristic sequence of any generating set of any finite dimensional unital algebra is proto-characteristic. And so given certain correct sequence, proto-characteristic sequence, we could always find out an algebra with the following, with a characteristic sequence equal to this proto-characteristic combinatorial sequence, and the length is the last term. So why we need such a result? For example, when we would like to study feasibility of length. So when we want to check what are the length values that could be non-associative algebra. And here we arrive via previous construction, we arrive to quite surprising results. For example, here we have maximal length according to our bound with Dmitry. But say if I take value maximal value -1, it is not realizable. And then we have a gap going up to that particular number, 3 multiplied by this power of 2, again gap, and another realizable number. And if you start from below, then realizable number is n divided by 2, but still there is a certain open problem here about existence, about what are the gaps in between. I will not go into the details, and in fact, my time 2 minutes. So I will finally mention quadratic algebra. Well, quadratic relation give us algebra, and the following bound for the length of algebra, we consider well-known Fibonacci sequence, important in combinatorics and in all parts of our life. For example, structure of one is parameterized by Fibonacci. But if we deal with finite dimensional quadratic non-associative algebra, then it also appears here mainly as an upper bound. So there is a following upper bound for the length of non-associative algebras, which are quadratic, using Fibonacci number. And this bound is achieved. And say for cubic algebras, we don't have such a bound from that cubic algebra, and I will skip some details on feasibility of algebras, but I just would like to finish with the following two problems, which are in fact standing for considerable time. So computing the length of matrix algebra in whole generality is open, so-called path. And the analog of Papachena bound in non-associative case where you use 2 parameter is also open. Yeah, maybe I stop here. Thank you.
Many thanks, Alexander. So I would like to start the questions session. Any question? We would like to thank again our speaker, Alexander. My personal congratulations. Very nice talk. Thank you very much.